All right, so we'll begin with example 2. We have a rectangular prism, a tank. It's a rectangular prism. Water is going to exit from a small hole at the top, so right here, that hole. Calculate the required work to pump the water out of the top. Assume that the tank is full. And then we're told that the density of water is 1,000 kilograms per cubic meter. So this is exactly why we talked about this box sort of idea here, in that gravity only depends on the weight of that the mass of the object that you're moving and how far you're moving it. Okay, so we can figure this out just by lifting this up really easily. So we're essentially going to do the same thing here. We're going to take something and break it up into lots of little chunks and then figure out the amount of work to lift each individual chunk. So over here, what we're going to do is essentially, we would conceptualize this by splitting this tank up into lots of little rectangular prisms, little rectangular slabs. And then we would essentially solve the problem by thinking about what is the total amount of water, what's the total volume of water in this bottommost slab. Well, we would have to take the dimensions here, which are 4 by 8. I won't write x, I'll do 4 by 8. And then we'd have to think about what's this thickness. Well, it depends on how many little slabs we break this up into. So it's going to depend. This is going to be, let's just call this dx. Or if we want to be really concrete here, what if we split this up into 5 slabs? And did I do 5 slabs? 1, 2, 3, 4, 5. There we go, 5 slabs. So if the total height here is 5, then each slab has a width of 1. So the volume of water is 32. So we need to know what's the mass of that amount of water? Well, we would multiply then by the density rho. So now we essentially have a block that weighs a certain amount. It weighs 32,000 kilograms. So now it's exactly like this problem over here, where we know how much the slab weighs and we know how far we have to lift it. So for this slab here, this bottommost slab, this has to be lifted up here. Okay? So in this case here, we can just assume, let's just say that we are considering the slab to be at the very bottom. So we're going to say it has to move a full 5 meters. So we'll multiply by, well, actually, before I do that, I'm getting a little bit too far. What this tells us right here, my apologies for skipping a step ahead for a moment there. This tells us the mass. I know I said that, but let's write it down. So before we lift it, we need to think about what is the force of gravity acting on this mass. Well, the force of gravity acting on this mass would be, well, we have to multiply by g, the acceleration due to gravity. So now this full thing right here, everything in the box, this is the force acting on that, let's say in quotations, slab of water. So now to figure out the work, we would multiply this by the distance that we have to move. So I'll just write this out as multiply by the distance to move, the distance that we want to move it. Well, we could treat that to be 5, for instance, since we're considering the bottom slab. But you can see exactly why we want to split this up into lots of little slabs, because really only this very thin layer at the bottom is being lifted anything close to 5 meters. Because this slab right here, if I consider another really small slab, this one here is being moved closer to 4 meters. And then the slab in the middle here is being moved closer to 4.5 meters in order to exit the tank. So really, it's varying continuously. And that's exactly why this quantity of work needs to be calculated by using an integral. So this procedure that I just did here is exactly what is listed right here. We first begin by finding the area of the cross-section, multiply by the thickness to find the volume, multiply by the density to find the volume, to find the mass, I meant to say, find the mass. Then you multiply by the acceleration due to gravity to find the force acting on that volume, that mass. Then you multiply by the distance to move to find the work needed to lift that slab. Then we use the integral to essentially figure this out for every single little infinitesimally small slab and sum them all up. So let's go ahead and do that. So a lot of this will be a reproduction of what we just did, but it's a little bit more precise. So what I'm going to do is I am going to draw a representative slice. Okay? You can draw this as the actual rectangle if you'd like, or you can just draw a line if you like to think about things more abstractly, whatever. Okay, so what we're going to do here is we are going to say that the bottom of this tank, let's say this bottom here, let's say this is y equals 0. Then we don't want this calculation that we're about to do, we don't want this to be valid at a specific value of y, say like 2.5 meters. We want this to be arbitrary but fixed. We want this to apply for any slice. So let's just go ahead and say that this distance is some y value. We're just at some height, something between 0 and 5. Maybe it's 5, maybe it's 0, maybe it's 3.21, something like that. So we'll start off with this setup. So step 1 is to find the area of this representative slab. Well, this is 4 times 8. So this is meters squared. So this is 32 square meters. The volume here would be the thickness. So for these problems, if you want to actually draw a little rectangle, if it helps you, if you want to draw this and think of this as some little rectangular prism with some perceptible but very, 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 very small thickness, you would want to call this dy. So doesn't matter to me how you choose to do it. I generally just draw a straight line. I don't give it a thickness because I know I'm already thinking of it as having a thickness. But as a reminder, when you're first learning it, it's good. So we have dy, its thickness. So the volume of the slab would be 32 dy cubic meters. And let me make that look a little bit more like a y and not a g. There you go. So then the mass, of course, we use the given density. So I'll just write this as 32 rho dy. We'll just multiply by that. So this becomes now kilograms. After mass, we want to know the force acting on that slice, so we would multiply by g. So I'll say 32 rho g dy, and the units of force are newtons. After that, we have the work acting on this slab. So we have to think about what is the distance this slab must move. Well, the distance the slab must move is to this height here. So we know the full height is 5 meters. And if this height that we're currently at is y, then that means we have exactly 5 minus y meters left to lift. So the distance that this current slab, resting at an arbitrary height of y, must move or be lifted to is 5 minus y meters. So we would take our previous line force, 32 rho g, and then multiply by 5 minus y. You'll notice here that I'm sort of like inserting the rho here. I'm not multiplying it at the end. Similarly for g, I inserted it here. I didn't put it in the front or the back or anywhere else. That doesn't really matter a ton where you put it, but I am thinking of this result ultimately going into an integral. Because all of these calculations that we just did, these are all for that single arbitrary slab of water. This is not for the total. So because all of these are just for that single slab, we then have to import this into the integral, and the integral will actually give us the total work. So that's why I'm gonna when I integrate this, I'm thinking of all of my constants being in front, my function that I'm integrating, and then of course our differential is always at the end. So I'm sort of building my integral in my head. We just don't insert the integral until the very last line here. So the total work would be doing this process as y continuously varies from 0 to 5. So I'll keep my constants out in front of the integral. I'd have my integral. And then this was being done as y varies from 0 to 5. So the total work is exactly that integral. Okay. And for these problems, I'm not going to go through and do the integration itself unless the integration is particularly interesting or difficult. So we'll just set it up, because really the new thing that can be challenging is how to think about this procedure and how to draw the appropriate diagram. Example 3 is a really quick follow-up example, so we'll do this in the same video. What if the water exits through the spout? So the spout is exactly 1 meter above what we did here. Well, what will change here is, well, not a ton. We can think of this value here. This is 1 meter above the top of the tank, so this is 6. So the distance that this must move now is no longer this distance. It must be moved all the way up to this height. So we can erase this little line segment, or this little measurement arrow, and put it there. So this distance is no longer 5 minus y, it's going to be 6 minus y. So what does that change? This only changes right here. That's the only thing. So our total work here would be the same exact integral, but with that one small change. So this would be 6 minus y. One thing that a lot of people do want to also change is there's this temptation to change this upper bound to a 6. And I can understand why, but really the water is really right here. We're really thinking of the water as living here. And there's always the argument that yes, there is water in this spout too, and it is being lifted up. You are correct. So shouldn't we have to integrate this little amount? And you know what? Sure, In the grand scheme of things, yes. But really, that volume of water, the cross section right here, is frail in comparison to what's going on here, and we are already describing this total amount of water lifting this amount. And what I can say is when you are working against gravity, gravity is a conservative force. So what that means is it doesn't actually matter on the precise path that you take. So for instance, if I have something start here, a certain mass, and I move it up here and I move it around and I go all underneath of itself, as long as I stop here, it's exactly the same amount of work as if I were to go directly up. So the fact that that gravity is conservative really means that this is quite negligible. Okay.